some joint work with Vitaly Feldman and Kunal Talwar, who are at Apple, and Hui Nguyen, who's at Northeastern. And this is actually not a work on streaming or on Johnson Lewis Strauss. It's on something related to differential privacy. So here's the setup, or here's the motivation, right? So a lot of us have smartphones, and on these devices, we depend upon some nice features like autocomplete and spell correct. Okay, automatic spell correct. And here's an example of a patent that you can find online, filed by Apple, which the part that's zoomed in on the bottom right says, systems and methods are disclosed for a server. The server is them, learning new words generated by user client devices, namely our phones, in a crowdsourced manner. Crowdsourced manner means us, right? So the point is, if you want to have these systems that do autocomplete or automatic spell correction, you're going to take data and you're going to train ML models using that data, and then that ML is going to let you do this kind of spell correct and autocomplete. But you need the data. And where's the data coming from? Well, there's that word there, crowdsourced, which basically means us, right? We are giving them the data. So the idea is, well, if you want to know how to predict what people are going to type in text messages, I want to have lots of examples of text messages. So how about every time someone sends a text message to their friend, a copy is also sent to the server, and then the server can learn from our data, right? So here's the here's the picture. So there's device 1 up to device n. Let's say each one has the most recent word that they texted to their friend. And then there's the server, and you're texting that word to your friend, but you're also sending a carbon copy to the server. So the server sees all the text messages. And now the server wants to know various things about what it's seeing, like what's the word distribution amongst devices. So let's say I want to know histograms. F sub x is just how many devices just texted the word x. I want to know that for every x. So this sounds easy enough, right? You send a copy of each text to the server, and then the server knows everything, so it knows the histogram. But there's a constraint, which is privacy. Do you really want phone manufacturers to read all your texts? Okay, probably not. But if you go back to that patent, actually, I mean, they're very aware of this issue, and they talk about privacy all over the patent. They talk about local differential privacy, a differential privacy system, privacy budget, blah, blah, blah. So they have a way around this, and what is that? And that's what this talk is about. I mean, this talk is not about any particular company. This is a general, theory talk, but this is we're going to talk about an approach to get around this. And the basic idea is that you're going to send randomized messages. You're not going to send your true data to the server. You're going to add noise to your data, whatever that means. We'll see it in a second. So here's the toy, picture. So let's say that I'm texting a picture to my friend. And this is a picture of me drinking from a baby bottle. I don't know if this is like, are baby showers, like in baby shower games, a big thing in Russia as well? Or is this just a very American thing? I don't know. Someone tell me.
I haven't been living in Russia for a long time, but I think it's an American thing.
It's an American thing. Okay, well, right, at least in the US, when you're expecting a baby, the baby's not born yet, you throw a party, you have a baby shower. And there are just all kinds of silly games that you play. And one of them, this was actually right before my daughter was born. The game was who could drink a full bottle of apple juice from a baby bottle the fastest. And it's not that easy. I found it very difficult to actually get juice out of the bottle. I guess I don't know how to suck properly the way a baby does. But anyway, so here's that picture. And here's so I'll send the true picture to my friend, but I'll send a noisified version to the server, right? So here are various versions of that same photo with more and more noise added, okay? And here it is with lots of noise, okay? And what's the idea? How is this useful for the server, right? At the end of the day, the server wants to learn things about what we're actually talking about or what we're actually sending. And the idea is, imagine now, if only one person in the world is sending this photo or is sending this text, okay, then the server won't learn it, which maybe it's okay, because if it's a very rare thing, then maybe it's not interesting for the server to learn. But if it's not a rare thing, if this particular picture went viral, for example, the server probably wants to learn that. So here's the idea. Everyone who's texting their friend will send a noisified version to the server, but the noise that's added is independent across devices. So everyone's adding independent random noise. And then some people are sending that picture, some people aren't. Some people are sending a picture of a cat, okay? But the point is, what the server wants to be able to do is collect all these messages and then notice that this picture of me drinking from a baby bottle is popular, but in a way where it doesn't actually know who sent the picture, right? It doesn't know, like, let's say that some of these are actually different. A few people, 1% of the people actually send a picture of a cat or something. The point is, if you take all these images and you average them, for example, I mean, averaging is not necessarily the best thing, but you average them, then you'll be able to see something that looks like me drinking from a baby bottle, but you won't know like which majority of people actually had this picture, right? You'll just know that a lot of people had it, but you won't know who. So privacy is maintained in that sense. So the moral of the story is, you can hope to have each individual message look like garbage to the server, thus protecting individual privacy, but the server can still extract useful information in the aggregate by aggregating all messages from devices and extracting useful information from the aggregate. This is like the goal. But before we can talk about achieving that goal, we have to define what does privacy actually mean? So for example, here's that same picture of me drinking from a bottle twice. On the left, I added a ton of noise. And on the right, I applied some standard like signal processing algorithm called wavelet denoising. You don't need to know what it is for today. But after I applied that wavelet denoising algorithm, on the right-hand side, it's not a perfect picture, but you can tell a lot of stuff. You can tell that it's a picture of someone's face drinking from something that's probably a bottle. You can tell that they're wearing a jacket with a collar. You got a lot of information out of it from this individual message. And the point of privacy was that you're not supposed to be able to tell anything from an individual message. You should only be able to tell things from the aggregate. So, at least this seems to violate what I wanted privacy to mean. So you have to be very careful with the definition. And then once you have a definition, a mathematical definition, you can then try to prove theorems to say that some algorithm, some mechanism achieves privacy. So you have to be careful with the definition. Okay, so here we're going to use this definition of local differential privacy. And the idea is that the device is going to send a random message that is only weakly correlated with its data. Like I'm going to add a ton of noise. Okay. One individual device's message will look like random noise, but the server can extract signal from the aggregate. That's already what I said before. Here's the privacy definition, okay, which is differential privacy. So what does this mathematical definition mean? It means that for any device, for any smartphone out there, let's look at a possible message M that it could send, okay? And let's look at two different pieces of data that it could have. So X might be a picture of me drinking from a bottle, and X prime is a picture of a cat. There's two totally different data items. And what we're looking at is the ratio of probabilities. What's the probability that this phone sends M given that its data is me drinking from a bottle versus what's the probability that it sends this message M given that my text was a picture of a cat? And the ratio of these probabilities should be at most e to the epsilon. And if it satisfies this, we say that if it satisfies this for all I and for all M and for all different X and X prime, we say that the scheme provides epsilon differential privacy. Epsilon is usually called the privacy loss. Okay, why is it called privacy loss? It's because the bigger epsilon is, the more privacy you lose. In particular, if epsilon is 0, you lost no privacy, right? What does it mean? It means that the ratio of probabilities is at most e to the 0, which is 1. And of course, I could have swapped X and X prime. So it's at most 1 and it's at least 1. So it is 1. So what that means is the message distribution is independent of X, is independent of your data. Well, if you're sending messages that are independent of your data, then they're private. By any kind of intuitive notion of privacy, that's perfectly private because you're not revealing anything about your data. Okay. But on the flip side, the server, the server is not learning anything because if your messages are not correlated with your data, then what's the point of the message in the first place, right? So epsilon equals 0 is perfect privacy, but of course the server learns nothing. And then you could hope that as you increase epsilon, as you're willing to allow more and more privacy loss, the server can get more and more utility and learn things, okay? So that's the trade-off that we want to understand. Two regimes to keep in mind. epsilon much less than 1. So that means e to the epsilon is roughly 1 plus epsilon, which means these probabilities are almost all the same, but they're not quite the same. And then there's the large epsilon regime, which is what's usually deployed in practice. Large epsilon means worse privacy. So why is that the one that's deployed in practice? Well, as I mentioned, there's a fundamental trade-off between utility and privacy. Utility is the quality of the knowledge the server is able to learn from the messages, and privacy loss, which is this epsilon parameter. So if these companies didn't care at all about privacy, then I want to maximize my utility, right? I want to learn everything because I can use that to deliver better products. But of course, the companies do care about privacy, so they have to understand the trade-off between these two things and choose some point on the trade-off curve. Okay, so they choose large epsilon because they want to have high utility. Okay, that's why they choose large epsilon. But why is that justifiable? If you choose large epsilon, it's like, well, your privacy sucks. How is that acceptable? The silver lining is that there's something called shuffling, which improves privacy automatically. I won't really get into it too much, but basically what shuffling says is, what if we change the model slightly? And I don't send my randomized message directly to the server, but I send it to an intermediary server. And that intermediary server has only one job, which is it collects all the end messages from the end devices. It applies a uniformly random permutation to them, and then it sends that to the server. So the server still sees the same messages, but because they're permuted, it doesn't know who sent what. It loses that information, who sent what. And you can show that you can get quite good improvements so if in the original non-shuffle model, you had a particular epsilon, once you shuffle, you automatically get a new epsilon that's better, okay? There's something about approximate DP, which I'm not gonna get into, but basically the point is like shuffling lets you justify using large epsilon in practice. So that's all I'll say about that. So before going further, our particular problem for today is the following, the histogram problem. Each device holds some data xi from a set of size k, a finite set of size k. This then implies a frequency histogram, which is f sub x is the number of devices where that device is holding data item x, and the server wants to learn the histogram. Okay, of course, it's not going to learn it exactly because there's some utility loss due to the fact that we are maintaining privacy. There's some noise. So the server just wants to recover some f tilde that is close to f. Close, we're going to measure as the mean squared error, which is just the average squared distance between fx and f tilde x. And of course, this is a random variable because the scheme is randomized. So we're going to try to minimize the expectation of this quantity. And overall, there are 5 things that we're going to consider. So, and for all of these 5 things, we want to get the quantity to be as low as possible. So we want the privacy loss epsilon to be as low as possible. We want the utility loss, which is this mean squared error, expected mean squared error, to be as low as possible. Communication. Each device has to send a message to the server, which is which takes some number of bits. How long is the message? Ideally, I want that message to be as short as possible because it uses as little bandwidth as possible. The server time also matters, right? The server receives these end messages, and it needs to run some algorithm to process those end messages from the end devices and come up with an f tilde based on that. And there's also the device time, which is given that I have some message xi, I'm device I need to then do the correct, sample from the right distribution over messages to produce a message mi given xi, okay? And I want that device time to be fast. So I want all these things to be as small as possible simultaneously. Before I tell you about our contribution, let me just give you a little taste of what's already out there. So a simple scheme that's already known is called randomized response. And let me actually tell you exactly how it works and how you would analyze it, because that's it's going to be helpful to understand where our scheme is coming from. Each device sends its true item x with probability e to the epsilon p. Otherwise, it sends a uniformly random other item such that any other item is sent with probability p. What is p? Well, there's really only one p that you can choose for this sentence to make sense, right? Because the probability that you send some message is 1. What's the probability to send some message? Well, you either send your true item, which happens with probability e to the epsilon p, or you send an item which is not your true item. Each one of those has probability P, and there are K minus 1 of them. So this sum has to be 1, which tells you what P has to be for this to make any sense. Okay, so that tells you how the device behaves. How does the server behave? Okay, the server needs to estimate frequencies. So I'm gonna, as the server, do an unbiased estimator. Okay, so I want the expectation of f tilde to be f. So here's what I'm gonna do. For each message mi, I'm gonna add alpha plus beta to my estimate of f tilde x if mi equals x. Otherwise, if mi is not equal x, I'm gonna add beta. Okay, well, if xi equals x, the expected contribution of that message to my count is alpha times e to the epsilon p plus beta. Right? It's like, what's the basically, if xi equals x, what's the probability? What's the expectation of? Okay, well, I'm always going to add beta no matter what, right? I always add beta no matter what. The question is, do I add alpha or not? I only add alpha if mi happens to equal x, right? So if xi equals x, the probability that I do add the alpha is e to the epsilon p. So my expected contribution to f tilde x from this particular device is this quantity, alpha e to the epsilon p plus beta. If xi is not equal to x, then my message will be x with probability only p. So then my expected contribution is alpha p plus beta. And by the way, I mean, this e to the epsilon p versus p is exactly because I want to satisfy differential privacy, right? Differential privacy says the ratio between probability of a message being sent should never be more than e to the epsilon. So this is, this is basically private by design. Okay. And of course, if I want this to be an unbiased estimator, that means alpha e to the epsilon, there should be a p there, my apologies. Alpha e to the epsilon p plus beta needs to be 1, and alpha p plus beta needs to be 0. I have 2 equations and 2 unknowns. So basically that determines what alpha and beta need to be. And now the scheme is fully determined. Now you know exactly what the server does. You know exactly what the device does. It's done. And now that you know what the scheme is, you can analyze its variance. And that lets you get a handle on its mean squared error. And the punchline qualitatively is that this happens to have low communication, right? At the end of the day, your communication is just an item from the universe, which is log k bits. It's very fast for the server and the device to do what they need to do. And if you actually analyze the variance, you can show that the utility loss, the mean squared error, is pretty far from what you would want to see. Okay, so that's randomized response. I'll do one more before I talk about where ours fits in. Another simple scheme is called subset selection. Okay, it's due to bargain Yi. And each device, what they'll do is they'll send a random subset of the universe of size d. Okay, so the number of bits is roughly, d log k bit, or log of k choose d bits, which is roughly d log k bits. Okay, so now what's the probability that a particular set is sent? From all the sets that contain x, any one such set will be sent with probability e to the epsilon p. If S does not contain x, it'll be sent with probability p. Again, the probability that I send something is 1. Well, how many sets are there that contain x? K minus 1 choose d minus 1. Each one of those has probability e to the epsilon p of being sent. How many don't contain x? That's k minus 1 choose d. So this thing has to equal 1, so p is determined. How does the server estimate f tilde given f, or f tilde x given x? How does it estimate f tilde x given the messages? Again, for each message, I'll add alpha plus beta if the message is a vote for x, if x is contained in mi. Otherwise, I'll only add beta and not alpha. I can write down if xi equals x, what's the expected contribution? If xi is not equal to x, what's the expected contribution to the count? Again, I have 2 equations and 2 unknowns. I solve them. I can figure out what alpha and beta are. Now that I know alpha and beta, the scheme is determined. I can compute the variance and get a handle on the mean squared error. That mean squared error will be a function of d. Remember, these are sets of size d. And then I'll compute a derivative, set it to 0, and basically optimize. I'll choose the best d to make the mean squared error as low as possible. And if you do that calculation, d comes out to this, roughly k. It's proportional to k. It's k over e to the epsilon. Okay, so if you think of epsilon as being a constant, D is proportional to K. So my message is like, think of e to the epsilon as 100 or something. So D is like K over 100. I'm going to send 1% of the universe. I'm going to send a set of size K over 100. That's a big message. That's like K bits, right? So whereas randomized response was only log K bits, here I'm sending something like K bits. Okay. The pro is that you can prove a lower bound. You can show that this actually achieves the optimal privacy loss, utility loss trade-off. For any fixed epsilon, this scheme gets the best utility loss possible, even if you don't care about computation, you don't care about communication, just information theoretically. There's no way to get better mean squared error than this, but it has exponentially worse communication than randomized response. And just the server, just to read all the messages is really slow. So I mean, the runtime on the server is also not great either, and neither is the device runtime. So those are two schemes. And now let me describe a meta approach, which is where our scheme fits in. So a meta approach is as follows. There's a message space Y. So for example, in randomized response, so message space just means like any message you send is always an element of message space. So in randomized response, message space was just the universe itself. In subset selection, message space had size K choose D because it's all the size D subsets of the universe. Okay. In the meta approach, I'm going to associate with each X some subset of message space of some fixed size little s. These are what I call the preferred messages for little x. I prefer to send an element of SX. And also I'll have a bounded intersection property. For any two different elements of the universe, x and x prime, the intersections of SX and XX prime will be equal to L. So this is some kind of design thing, some combinatorial design. Okay. So for example, so in mechanism, for any element of message space, I'll send that message with probability P if Y is not a preferred message, if it's not in SX. Otherwise, I'll send it with probability e to the epsilon P if it is a preferred message. So for randomized response, little s was 1, and S sub x was just x itself. It was just a set containing x itself, right? I prefer to send myself. And in randomized response, little l was 0, right? The preferred message for x and the preferred message for x prime, there's no overlap. In subset selection, little s is, I guess, k minus 1 choose d minus 1. It's basically the number of size D subsets which contain me. And you can also write you can write down explicitly what L is. It's not 0. Okay, I guess if the set needs to contain both x and x prime, it's probably little l is something like, I guess, k minus 2 choose d minus 2 or something like that. Okay, good. Note again, the probability that I send something is 1. What's the probability that I send something? Well, there are little s preferred messages, and there are y minus little s non-preferred messages. So P is equal to something. Okay, it's basically determined what P is. And the server will estimate the frequency of item X as follows, just like before. For every message, if it's a preferred message, I add alpha plus beta. If it's not a preferred message, I only add beta. I want to make sure that when xi equals x, the ith sum end has expectation 1. When it's not equal to x, it has expectation 0. In other words, I get, again, two equations with two unknowns. I can solve and I get alpha and beta. And alpha and beta only depend on S and L and epsilon. And they also depend on the size of message space on Y, because P depends on the size of Y. Okay, so great. Now let's talk a little bit about the variance. So by independence, the variance of the estimate is the sum of the variance of the contribution of each individual message. Okay, and you can write down basically explicit expressions for what the contributions to the variances are from each message. And then you can do some math. And none of it, I don't expect you to follow all these calculations. There's nothing really that deep that's happening here. They're just calculations. But the key takeaway is I can write down an explicit expression for the mean squared error. And it's only a function of L, S, epsilon, and the size of message space. Remember, S is the size of the preferred message list. Little l is the size of the intersections. I've highlighted, I mean, both these two things being added in total are the mean squared error. Just take my word for it. The one that's highlighted in teal, in blue, is kind of the dominant term. The other term, let me ignore for this talk. Okay. And the takeaway is that the mean squared error increases as a function of these ratios. So if I look at the ratio L over S, ideally I want that to be as small as possible. Okay, because that makes the mean squared error smaller. And also if I look at the ratio Y over S, remember S is the size of the preferred message list, Y is the size of message space. I want Y over S to be as small as possible. I also want the size of Y to be small because the length of a message, right? For me to send a message, I have to tell you which element of message space am I sending. That's log Y bits. So if I want log Y to be small, that means I want Y to be small. So I also want Y to be small. Okay. Good. And now this is basically just a combinatorial, this is just combinatorics. There's no more, we don't have to think about commutation for now, right? If we just want to minimize the size of Y and minimize these two ratios, it's a combinatorial question. And we use a known idea in combinatorics, okay? And the known idea is basically to use linear algebra over finite fields, okay? So where's this, before I say what we do, here's kind of the thinking, the intuition. Okay. Let's now think about Q as a prime, and let's think about FQ to the T. So all length T vectors with elements in FQ. Okay. And let's think that our universe size K is equal to Q to the T. Or let's say K is less than or equal to Q to the T. And I'll just have some injection from elements of 1 to K into elements of FQ to the T. Okay. So I can think of every element in my universe, every word in my dictionary, as a vector in FQ to the T. And its preferred message list will be the subspace orthogonal to it. Okay. Which is a subspace of dimension T minus 1. It has codimension 1. Okay. And now the nice thing about that is they all have the same size. All subspaces in FQ to the T of some fixed dimension all have the same size. In particular, since they has dimension T minus 1 in this case, they all have size Q to the T minus 1. And what I'd like to say is if I have two elements in X and X prime, their orthogonal subspaces are different subspaces. So when I intersect them, I'll get a subspace of dimension T minus 2. So all the intersection sizes are uniform. They all have size Q to the T minus 2. So basically L over S will be 1 over Q. S over Y will also be 1 over Q. And Y has basically the same size as K. And if everything I said right now were true, that would actually be perfect. That would turn out to be a really good thing for the variance. So maybe I'll, just to see if anyone's paying close attention, what I said is not true. There's something wrong with what I just said, right? So does anyone see anything wrong with with the construction I just proposed? Very, very minor issue, but it's a real issue. No takers?
I think it might have been a little. Yeah.
Go ahead.
I'm just saying it was a little hard to follow without you were saying symbols but nothing was on the screen. So I found.
Oh yeah, okay. Yeah, sorry. Okay, yes. So yes, and I will write it down, but I'll write down what we actually do. But yeah, so basically, I'm just going to pretend that every element of my universe is a vector in FQ to the T. It's a T-dimensional vector over FQ. Its preferred message list is the set of orthogonal vectors, right? So, for any Y that's orthogonal to X, it'll be sent with probability e to the epsilon P. But if Y is not orthogonal to X, it'll be sent with probability P. And the point is, this subspace, this orthogonal subspace has dimension T minus 1. So little s is now Q to the T minus 1. And if I have two different X's, I have X and X prime, which are different, there are orthogonal subspaces, their intersection is a subspace, right? And their intersection is a subspace of dimension t minus 2. So basically now I can talk about ratios of S and L, because one is a dimension t minus 1 subspace, one is a dimension t minus 2 subspace. But I mean, so the problem here is that x and x prime might not have different orthogonal subspaces, because x prime might be a scalar multiple of x, right? In which case the orthogonal subspaces are exactly the same. So you don't get the uniform intersection properties of these preferred message lists. So what we're going to do is use projective geometry, okay, which is just a fancy way of saying the following. First of all, we pick the prime q to be e to the epsilon, because when you run through the mean squared error analysis, the variance analysis, that turns out to optimize the mean squared error. And a projective point in fq to the t is simply a non-zero vector in fq to the t whose first non-zero is a 1, right? So the way that I fix this issue of like two different orthogonal subspaces being the same is I'm going to say, well, I'm going to enforce that x is not equal to x prime by saying that I'm going to view x as being a canonical vector in fq to the t. Namely, its first non-zero entry is a 1. Okay, so if x is a canonical vector and x prime is a canonical vector, their orthogonal subspaces are definitely different if x and x prime are different. Nothing too complicated here. You can show that the number of projected points is exactly q to the t minus 1 over q minus 1. Why? Just because, well, there are q to the t vectors in this space in fq to the t. I subtract 1 because I exclude the 0 vector. And then every vector that remains has q minus 1 different scalar multiples of it, non-zero scalar multiples. So I divide by q minus 1. And I'm going to identify my universe with projective points. And the preferred message list is simply the projective subspace orthogonal to x. Namely, it's the set of all projective points u such that x dot u is 0 mod q. And again, you know, it's not too complicated to compute the size of a projective subspace of various dimensions. So that gives you a handle on what S and L are. And the bottom line is, if you do this, you get the nice SL and size of message space that you wanted.
Jelani?
Okay. Yes.
Can I ask a question? I'm a little confused. So Q is approximately e to the epsilon. So are we thinking of epsilon as being largish? Like, so it's...
Yeah, so we focus our attention on the case where epsilon is like the case that's usually deployed in practice for this particular problem, which is epsilon is larger than 1. From what I hear talking to the people in the real world who actually work at companies that use differential privacy for this particular problem, it sounds like epsilon is usually like 5 or 6 or something like that, in which case e to the 5 is about 150. And I think 151 is prime. Does that answer your question?
Yes, thank you.
Any other questions? Okay, so we can continue. So here's now a table of results, including our own, but also prior work. So there's communication utility loss and server time. Let me first focus on utility loss, which is the numbers in it. So randomized response, the key thing to note about randomized response is the utility loss. If you distribute the n over the parentheses, it has an n times k. N is large, n is the number of smartphones in the world. K is large. K is the size of like the number of words in the dictionary or something. So K is large. So n times k is really large. Whereas if you look at some of the later ones like rapport and subset selection, there's no times k, right? And in fact, it's been proven by Yi and Bar, 6, that this expression 4n e to the epsilon over e to the epsilon minus 1 squared is actually optimal. And when I say optimal, I don't mean the usual theory CS big O optimal. I mean actually the constant 4 is even optimal. Everything about this expression is optimal. Okay. The downsides are, if you look at the communication, rapport and subset selection both have communication that scales up linearly with k, and the server time also has n times k, whereas randomized response is really fast, it's n plus k. The communication issue was fixed recently in pi rapport, so it was only log k bits of communication, with optimal utility loss, but the server time is still like the min of k squared and n times k, which again, k squared is not great, n times k is not great. Okay. So these were somewhat addressed by later works of Hadamard response and the recursive Hadamard response, which both get log k communication, which turns out to be optimal, server time, which is pretty fast, nearly linear, but the utility loss took a hit in the constant factor, so 8 versus 36. And I should mention that there's something to be said about getting the optimal utility loss. So a lot of these algorithms on the server side are very parallelizable. So imagine that I'm a big company, like I'm Google or Facebook or Apple or something. Now these companies, from what I understand, spend a lot of money on compute to provide the highest quality services and products that they can. Okay, like I want bigger and bigger ML models to provide better and better, quality search results, answers, whatever, or better autocomplete, etc. I, as a company, am willing to spend money on more and more machines to provide that compute power to get me better service for my customers. Okay. Which means that if I have a very parallelizable algorithm, okay, the difference between k squared and k, of course, is very huge. But like the difference between k log k and k, I mean, maybe I'm willing to like buy more compute to to offset the fact that it's a little bit slower, if it means that I get better utility. Because at the end of the day, utility is basically how good is my autocomplete, how good is my spell correct, right? Maybe that might be like sacred, right? I'm not willing to take a quality hit on my product. So maybe actually the fact that I have replaced the 4 with an 8 here is not acceptable. Because I mean, I can always offset the server time issue with more machines, but how can I get better utility loss? Utility loss is like a fundamental property of the algorithm. If you look at this expression, 8n e to the epsilon over e to the epsilon minus 1 squared, the only way to make, so basically, like maybe I can modify that by changing n, right? But n is like the number of people who bought an iPhone or something. Like that's not really something I can control, right? I can't spend money to change that. But I might be willing to spend money on compute. So that was kind of the motivation for us, was like, do you really need to sacrifice optimal utility loss to get really good communication and really good server time? And what we show, the scheme that I just showed you with this projective geometry, is that we actually achieve the optimal utility loss, including the constant factor. Our communication is log k, and our server time is worse by a factor of e to the epsilon. In practice, again, epsilon is like 5. So e to the epsilon is like 150. So our server time is worse by like a factor of 150. But again, all these algorithms are highly parallelizable. So maybe I'm willing to take that hit and just like buy more compute. Okay. So we actually implemented not only our algorithm, but like all the algorithms that you see on this slide, we implemented. Let me not get into explaining everything about these plots, but basically the y-axis is the error, the mean squared error. The x-axis means this is a randomized algorithm. So I ran it a bunch of times. I ran it like, I don't know, hundreds of times. And I looked at the empirical distribution of the error. And these are like the percentiles of the mean squared error. So x equals 50 is like, what was the median mean squared error over all of the random trials that I ran? And then 100 on the right is like the worst error I ever saw. Okay, so the key thing to note here is RR is randomized response, which, as you can see, has the n times k. In our experiments, I mean, randomized response is like, it has such bad error that it just skews the whole plot. You can't really even compare most of the other algorithms because randomized response is so bad. Okay, so now on the right-hand side, I do another plot where I just exclude randomized response. And you kind of see two things here. Hadamard response and recursive Hadamard response, those are the red and the green at top. Those are the two who had 36 and 8 in this table. They're noticeably worse than the rest. At the very bottom, the bluish green, the light blue is PG, that's our new algorithm. And the blue is a subset selection. That's the optimal, that's the algorithm that was already known that was optimal. And our curves are pretty close to each other. And the yellow one is a variant of our algorithm where you can trade off runtime for mean squared error. So if you go here, the very last row in this table, in the runtime for the server, you can replace e to the epsilon with any prime q you want. So like q could be 5 or 3. But then if you look at your utility loss, you pay an extra factor of 1 plus 1 over q minus 1. So in particular, let's say you set q to be 5. Instead of multiplying my server time by 150, which is e to the 5, which epsilon is 5, I only multiply my server time by 5. And my utility loss gets worse from optimal by an extra 25%. So instead of 4n e to the epsilon, it's 5n e to the epsilon. So that's the yellow curve, okay? Okay. In more experiments, again, basically, I mean, qualitatively, no matter kind of what we did, it was always the same story. Empirically, our new algorithm is optimal. I mean, that's what the theory suggests. And in practice, it really is. The curve is basically on top of the previously known optimal curve. The yellow one is kind of in between. And then the red and the green kind of swap roles sometimes. But basically, they're noticeably worse by a constant factor. That's the recursive Hadamard response and the Hadamard response. We also did runtime trials. So on my desktop in my office, with like a universe of size roughly 3 million, with epsilon being 5. We ran PyRapor, which was the previous state-of-the-art algorithm. We actually came up with a new, faster algorithm for PyRapor because the original algorithm in their paper would have been too slow to run in any reasonable amount of time on my machine. So we came up with a new algorithm for the previous state-of-the-art mechanism. And even with that new, faster algorithm, PyRapor took more than half an hour. Meanwhile, our new algorithm took about 37 seconds. If you run the variant of our algorithm that's only multiplies the runtime by 3, but has 50% worse utility loss, so basically instead of 4n e to the epsilon, it's 6n e to the epsilon. It ran in 6 seconds. And then the previous algorithms that were fast. They were still like, they were like a second, half a second. But like, you know, RHR and HR had noticeably worse utility loss by a constant factor. And randomized response is blazingly fast, but of course its utility loss is really, really bad, so you wouldn't want to use it. Okay. So I told you what our scheme is with projective geometry. I've shown you experiments showing that it's actually good in practice. It's not just the theory. But why is our scheme actually fast? So let me talk a little bit about the algorithm. And the idea is to basically use dynamic programming. So here's what you need to do, remember, in the meta scheme. So the estimate of the frequency of item x is the sum over all messages I of alpha plus beta if I is a preferred message, just beta if it's not a preferred message, which I can just write as alpha times the number of preferred messages I saw plus beta times n. The definition of preferred message is that it's a canonical vector u that's orthogonal to x. So this sum over I is the same as the sum over all canonical u such that u is orthogonal to x mod q of the number of messages equal to u. So y sub u, y is now a histogram over message space, where y sub u is the number of times I saw message u. Now, naively computing that sum would look as follows. For each x, I need to sum over all the canonical u that are orthogonal to x. It turns out they're exactly k over q such u's, and then add up all the y u's. So it's k over q time per x. There are k values of x. The total runtime would be k squared over q, which is roughly k squared over e to the epsilon. So that's quadratic time, which is not good. To go faster, we use dynamic programming. So we need a recurrence relation to do our DP. So let A be kind of a prefix. Let A be like a prefix of an element of fq to the t, a length j prefix. And let B be a length t minus j suffix. And let Z be an element of fq. Where furthermore, we restrict A to be to be such that its first non-zero entry is a 1. If it has a non-zero entry, its first non-zero entry must be a 1. So basically, A is like the prefix of a canonical vector that we're building up in the recursion. Now what I define is this f function, where f of a, b, z is the sum of all y sub u's, where the length j prefix of u, where u is canonical now, where the length j prefix of u is a, and if I take the length t minus j suffix of u and dot it with b, that's congruent to z mod q. So f tilde sub v is actually now alpha times capital F of a being the empty vector, comma v, comma 0 plus beta times n. And now, in order to compute this capital F of the empty vector v0, I need a recurrence relation. And we're going to find that there is a recurrence relation, and then we can use dynamic programming. And it's nothing, I mean, this is, now that I've said this, I think it's something where, like, if you just sat down for half an hour or not too long and just kind of understood everything I've said so far, you would be able to come up with this recurrence relation yourself, I think. And it's something that's not super complicated. It's basically like, I built up the first, so I'm trying to build up u, right? I've built up the first j coordinates of u so far, and I'm trying to extend it to the j plus first. And it's like, what can I append? What can I append to satisfy the dot product relations so far and the canonical constraints so far, blah, blah, blah. So it's not too complicated. Let me not dwell on it. If you then apply dp to this, you say, well, how many possibilities are there for A? How many are there for B? Of course, there are q possibilities for Z because it's an element of FQ. And then what's my runtime? What's my runtime to actually compute an element of the dp table? That's another factor of q. You're going to end up with kq squared t runtime and kq space. There's an observation you can do, which is that, remember now, in the recurrence relation, in the definition of f, the dot product has to equal z mod q, right? But if I scale b by gamma, and I scale z by gamma, and I say, look, actually, the dot product of that suffix with gamma times b has to equal gamma times z, that's the same thing. And I can choose gamma to ensure that b is a canonical vector. And I can use that to basically cut down the number of states of the dp, the number of states of the table I need to actually compute. So I can choose this zeta such that b zeta inverse is either canonical or the 0 vector, and that will cut down on the possibilities for b by a factor of q. And that will lead to kqt runtime and linear space. If you do bottom-up DP, where you also use the usual trick in DP where, like, this is some DP table, this is some DP matrix, and like one dimension, one part of the matrix only depend, the next slice, the next like dimension, the matrix only depends on the previous one. So I don't need to keep the entire DP table in memory the whole time, and I can use that to save a factor of q in my space as well. This is very vanilla dynamic programming, so I'm not going to dwell on it. But if you take the time to really figure out what's going on here, I assure you it's nothing super complicated, and it's just DP, and it's implementable. And in fact, we implemented it. It's all on GitHub. This is basically the main logic in the server reconstruction algorithm to do this dynamic programming. Fits. Oh yeah, I'm slightly cheating because there's a util call in the middle, but it's not a very complicated util call. But yeah, it's just some vanilla dynamic programming. Okay. It's also possible to trade off utility loss and server runtime, as I mentioned. So for any prime q between 2 and e to the epsilon, I can worsen utility by, actually it's a 1 plus 1 over q minus 1 factor, but speed up the runtime by an e to the epsilon over q factor. The basic idea is that I'm going to break up the universe, which has size k, into h blocks, each of size k over h. And the randomized algorithm of the device will do the following thing. It'll do randomized response to reveal the true block that X lives in with some probability. And if it does choose to reveal the true block with randomized response, then it'll do the projective geometry mechanism inside the block. Otherwise, if randomized response says, you know what, I don't want to reveal the true block, then it's going to send a totally random message in period, okay? And we call this scheme hybrid projective geometry response because it's a hybrid between randomized response and our new algorithm. And you can analyze kind of as a function of H, that basically determines the trade-off between the runtime and the, and the utility loss. What next? One thing that I kind of swept under the rug is, you need to make sure that the number of canonical vectors in FQ to the T is at least K. So you can basically treat your universe as being in correspondence with canonical vectors. So basically you need to choose T. Once you fix Q, you need to choose T large enough such that the number of canonical vectors in FQ to the T is at least K. And if you choose T to be something and it's not quite big enough, you need to round up to the next value of T. That means you round up to the next power of Q, which has costs. It basically means that you're operating over a message space that's a factor Q larger potentially than what you really wanted to operate over, which means your runtime is going to suffer by a multiplicative factor of Q. And your communication is going to suffer by an additive log Q bits. So one question is like, is there a way to come up with some mechanism that, basically the message space is denser? So basically my message space, could be, I could always choose a message space that's like has size, which is a power of 2. Then I only have to round up to the next power of 2 instead of the next power of e to the epsilon. And then I don't have this hit to my runtimes, for example, that are as severe. Another thing is that finding this approximate frequency histogram f tilde such that f minus f tilde has small norm is related to something called the heavy hitters problem. And there have been papers on locally differentially private heavy hitters. And the thing about heavy hitters is that basically, if the norm is L infinity norm, and depending on what error guarantee you want, actually the number of words in the universe that can actually be large, that can have large f, is sublinear in K. And if the number of words I'm trying to find, the popular words, if the number is sublinear in K, I can hope for an algorithm that runs in sublinear time to actually find them. And we have such algorithms. But the problem is that those algorithms do not get the optimal constant, like this factor 4 that I told you about. So one question is, can we get sublinear time locally differentially private heavy hitters that actually achieve the optimal utility loss with the optimal constant? And maybe the final question, which is beyond my control, is, is this going to be one day deployed on your smartphone? And I think, I think there are algorithms that solve this problem, that solve locally differentially private heavy hitters that actually are deployed, I believe. So I think that's exciting that, this is like T-theory CS that could actually like be on smartphones around the world. And these days there are a lot of them, obviously. So that's exciting to me, at least. So that's all I have for my talk. And I would be happy to take any questions from the audience.
So let's start by thanking Jelani. And if there are any questions, please feel free to unmute and ask the question or put them in the chat. Well, people are thinking maybe I'll ask. So when you say sublinear time, it's sublinear in what?
Sublinear in K.
Sublinear in the universe size, right?
Yes. So let's say that like so messages are being sent. Mm-hmm. So messages are being sent by devices, and I'm collecting those messages. Let me not count the runtime of that, because that might not all happen synchronously. And then once I've decided that I've collected all the messages, now I need to like run an algorithm. Okay, so let me be a little more careful. So let's say that I'm storing some data structures locally, and then every time a message is sent by a device, I want like a fast algorithm to update my data structure. Let's say, I don't know, like polylog time or something. And then now someone says, query, report to me the list of all the frequent elements in the universe. I should be able to do that in time sublinear in K. And I want to do that with the optimal constant in my utility loss.
Okay, makes sense. Thank you.
Any other questions?
So I have a very naive question maybe, but if we allow some kind of cryptography things, could it help, or it's stupid? For some reason it doesn't make any difference?
Yeah, so maybe this might be a question for Sophia, because I mean, I think in terms of differential privacy, the definition I gave here is like an information theoretic notion of differential privacy. And there have been works on like computational notions of privacy. That's something that I haven't worked on myself, and I personally know a little less about, but Sophia might know more about that.
So it's true. So basically, if you define privacy the way Jelani defined it, so local, everything that leaves your machine is already private, right? So it's called local privacy, and there's a centralized model where everything goes to the server and the server analyzes it, right? And then releases the statistics. So you can probably do many things more accurately in this model, right? But so in the local privacy model, you can also use MPC, secure multi-party computation, right, to implement it. But companies don't go for it. So like they basically, right now, what they're deploying is actually what the model that Jelani explained, because they don't want any responsibility. And I guess maybe there is also computational overhead. So like in principle, you're right, cryptography can help in implementing this, but that's not what the companies are doing, as far as I know. I don't.
Thank you. Any other questions?
What are the big questions in local differential privacy right now?
I mean, I must admit, I'm like a newcomer to this space. So, I mean, as you said when you introduced me, historically, I've worked mostly in streaming and sketching and random projections. So at least, I mean, problems that I'm interested in, that now that I've like learned a little bit more about this space, I think there are still some questions related to some like specific questions like mean estimation that I'm currently working on, and getting the good trade-offs, but while also having computational efficiency, like fast runtime, et cetera. But like more foundational questions that are open, or like complexity theoretic, well, yeah, that go beyond just like say an individual task and say something about, the world of privacy at large. Oh, okay. So actually, maybe one thing that I'll say, which is actually using privacy as a tool for other things. That's something that I've been interested in recently as well. So here I talked about using differential privacy because I care about privacy. But there have been a number of works recently, one of which I was involved in, but there are a bunch of others, and that started even before me. I'm a newcomer to this space as well, which is, suppose I have a randomized data structure, right? Normally with a randomized algorithm or randomized data structure, let's say Monte Carlo, what does it mean? It means that for all operation sequences of the data structure, the probability that I answer the queries correctly is at least 99%. But the order of quantifiers is like for all operation sequences, for all inputs, the probability that I work for this input is high. But if I have some interaction with the data structure, so I do update query, and then now based on the answer to that query, I'm like, that's an interesting answer. Because you gave me that answer, I now have these other updates and queries that I want to do. Now what that means is the second phase and the third phase, et cetera, of updates and queries are correlated with the internal randomness of the data structure. Because the only reason I did those updates and queries is because you answered the first query in a certain way, right? So how do I design, so all bets are off now, right? Like my correctness guarantees for my Monte Carlo data structure don't hold anymore, because the input is now correlated with the internal randomness. You're not allowed to look at the random coins of an algorithm and pick the input based on those coins. So how do I design randomized streaming algorithms, randomized data structures that support this kind of interaction and still are correct? And what people have realized is that you can use differential privacy to do that. Actually, your question was, what are the open questions in local DP? But this is just DP, this is not local. But how do I, so the main idea there was like, view the private database as being like the coins of the data structure. And then when you answer queries, you use DP to maintain the privacy, to hide information about your local coins. So you're using DP as a tool to design algorithms, even though your problem has nothing to do with privacy. So I found that to be pretty interesting, and there's been a lot of papers now kind of using this kind of idea.
Right, thank you. That was very interesting. Does anybody else have any questions? Yes, it seems like we're out of time. So
Okay, well, thanks for having me.
Thank you, Jelani. So
Okay.
this concludes our day for a conference for today. And tomorrow we're going to start, I guess I know my time, it's going to be 10 a.m. But look on the schedule to see what it is your time. All right, thank you, everybody. Bye.